Batteries, we all know them. They come in many shapes and sizes, but most importantly, they come at different voltages and capacities. Today, we will look at how to make sense of battery capacity and their different voltages. So here are a few different types of battery. A standard AA 1.5 volt alkaline cell, an 18650 3.7 volt lithium ion cell, and a 1.2 volt nickel metal hydride cell. The nickel metal hydride and the lithium ion cells are rechargeable, but the standard 1.5 volt AA battery is non-rechargeable. We have all seen the AA cell and probably already know its nominal voltage is 1.5 volts. The lithium ion or even lithium polymer cells are very common in applications that require higher voltages and higher current output, used commonly in laptop power supplies, smartphones, tablets, electric cars and more. When you purchase a battery, you usually see these ratings on the packaging or the battery itself. These are the capacity ratings of the battery. mAh stands for milliamp hour. Sometimes you will see AH or amp hour. Now the milliamp hour rating of a battery can give you a really good idea of the amount of time it will last before it is discharged and needs recharging. For example, when you see that a battery has a rating of say 2000 milliamp hours, for simple math, this means that you can draw 2000 milliamps or 2 amps from the battery for 1 hour, or even 1000 milliamps or 1 amp for 2 hours. Or even better, you can draw 20 milliamps for 100 hours from a battery with a 2000 milliamp hour rating. So this 1.2 volt nickel metal hydride cell has a rating of 2850 milliamp hours. So let's say I power a small torch that has three 3-volt LEDs that consume a combined total current of 60 milliamps. Whoa, wait a second. These LEDs require 3 volts, and a nickel metal hydride battery has a nominal voltage of only 1.2 volts. To get me over the 3 volts threshold, I need 3 of these batteries in series. Okay, so we will put 3 nickel metal hydride cells in series into our imaginary torch. Does this change our overall capacity? Well, no. The capacity rating is the same because our batteries are in series. The fact that they are in series has increased our voltage, but not the capacity. The story would be different if we had the batteries in parallel, but we'll get to that shortly. So we have our 3 nickel metal hydride cells with a combined nominal voltage of 3.6 volts. This means I will now be able to power the 3 LEDs that will consume the 60 milliamps. Okay, so how long will this imaginary torch last? So here's how we do the calculation. We are consuming 60 milliamps, and our total battery capacity, because it's in series, is still 2850 milliamp hours. So all we have to do is divide the total battery capacity by the total power consumed. In this case, 2850 milliamps divided by 60 milliamps gives us an answer of 47.5 hours. So our torch should light for 47.5 hours. That's pretty good, thanks to the excellent efficiency of LEDs. But not quite. Our math isn't wrong here. Our torch would certainly light for 47.5 hours, but only if the voltage stayed above 3 volts. The fully charged voltage of a 1.2 volt nickel metal hydride battery is 1.4 volts. Yes, I know, stay with me here. And a discharged or dead nickel metal hydride battery is around 900 millivolts, or 0.9 volts. So our total voltage here, if fully charged, to start with, is 4.2 volts, the 3 times 1.4 volt cells. In this case, I would have to use a 60 ohm resistor for each LED to bring it to its 20 milliamp current draw at 3 volts. As the batteries discharge, the voltage drops, meaning over time the torch will consume less current, and eventually the voltage of the batteries will drop below the required voltage of 3 volts to light the LEDs. This means that while our calculated answer gives us a great estimate of how long the batteries will last, it really involves a lot of complex math, and we have to take into account many more variables to accurately understand how long it will really last. Overall, it really depends on what batteries you are using, what you are powering, and in what configuration. It's fair enough for us to say If we aren't in a position that requires us to account for every milliamp and every other variable, the simple division of capacity by the current consumed will give us a good enough idea of how long a battery should last. One last thing I need to mention: if we connect batteries in parallel instead of series, the voltage will always stay the same and the capacity will increase. So instead of combining the voltages in this configuration, the combined fully charged voltage in this configuration is 1.4 volts, not the 4.2 volts like we had in the series configuration. In a parallel configuration, the voltage stays the same, but the capacity increases. So let's say I have two 3.7 volt lithium ion cells with a capacity rating of 2500 milliamp hours. Two of these batteries in parallel gives us the same 3.7 volt nominal voltage or fully charged voltage of 4.2 volts, but increases the capacity. Two of these batteries would give us a total capacity of 5000 milliamp hours. Again, in a series configuration, the capacity would remain at 2500 milliamp hours, but the voltage will instead be increased to a fully charged voltage of 8.4 volts, or nominal 7.4. And by the way, if you are wondering, you can also increase capacity and voltage by having series and parallel combinations. If you were confused by the nominal voltages versus the fully charged voltages, this is simply just the chemistry of each battery. A lithium cell's nominal voltage is 3.7 volts, but fully charged it is 4.2 volts. When you draw current from the battery, it will slowly creep back to its nominal voltage before then discharging to its considered discharge voltage of around 2.8 to 3 volts. Okay, so I hope you could make sense of all of this information. You can leave your questions in the comments if you need me to make any of this clearer. But if you did like this video, please give it a thumbs up and subscribe to the channel if you aren't already. There are many videos ahead.